I'm a researcher at the DCNet research group at the University of Leuven in Belgium. And today I will be talking, well, mainly about cookies, as the title gives away. And I will try to figure out who left open the cookie jar. So I'm sure, well, every one of you knows about cookies. Personally, I don't really know how to feel about cookies. So on the one hand, I think they're great because they allowed the web to become what it is today. So without cookies, we wouldn't have had, we wouldn't be able to log into any website. But on the other hand, the way that cookies were designed allowed them to be, introduced a number of vulnerabilities. For instance, there's a CSRF attack against, or there was a CSRF attack against OpenEMR, which is an open source medical records software. And this CSRF attack allowed attackers to expose millions of patient records. Similarly, in PHPMyAdmin, there was a CSRF vulnerability that allowed attackers to delete records. And then also in wireless routers, there were CSRF vulnerabilities. And these issues are all very recent, so they're from late 2018. And I'm sure that since then, a lot of new CSRF or issues related to how cookies are implemented arose. So on the one hand, well, we have the security, but on the other hand, cookies are also used for tracking users online. So there was a study by people from Clicks who found that when they analyzed the browsing behavior of 200,000 German users, they found that on 95% of the pages that they visited, there was a third-party request to a potential tracker. So I think, well, we can agree that tracking is very pervasive and that it's happening everywhere. So there are these, well, not so nice things about cookies, and users try to defend against these, or browsers try to defend against these. So on the one hand, we have the built-in browser options. For instance, in most browsers, it's possible to block all third-party cookies. There's a new standard being developed, or it's already developed and implemented, called same-site cookies, which is, I think, available now in most common browsers. I will come back to this one later and explain how it works. Then there are some other more advanced or more specific approaches. For instance, Firefox has a built-in tracking protection. Opera has an ad blocker. Safari has this ITP, Intelligent Tracking Prevention. And next to all these built-in browser options, there's also a bunch of browser extensions. And we, in our study, mainly focused on ad blockers and privacy extensions. So all these things are there and they work relatively well. So the concept behind it is relatively good. However, there's one main pitfall, and that is that all these policies can only work when they're correctly enforced by the browser. So we put this to the test, and we evaluated several different browsers and many different ad blocking and privacy extensions. And well, I will give a small preview of what is yet to come. So we found vulnerabilities or issues in most of the browsers, and we could bypass all of these browser extensions. So in this talk, I will start with a brief background and motivate why we did our research. Then I will be talking about the framework that we built to evaluate the correctness of these cookie policies. I'll describe the results, and then in the later part of this presentation, I will be talking about how we are extending this framework to also test other browser policies, both for security and for privacy. And finally, I will give a brief conclusion. So, well, I know that this is OWASP, but I'll just briefly go over some web fundamentals so that everyone is on the same page. So here we have a web page from domain A, which includes a resource from domainb.com. So what happens in the browser is the user visits domain A.com and it requests this HTML file, which will then be rendered. And the browser will see that there's a reference to this image tag, and it will then fetch this image. So that's all very basic. So now when we have HTTP cookies, so some important properties about them are that they are implicitly included. Usually they're used for authentication or identification, and they're also subjected to the same origin policy, which means that cookies of domain A can only be accessed and read and set by domain A, and the same for domain B. So when we go back to our original example, our browser will send along the cookies for domain A in this first request, and the second one will have the cookies of domain B. And because this request is to a third party, so from domain A to domain B, we call this cookie B a third party cookie. So how can things go wrong? One of the examples is cross-site request forgery. So it allows an attacker to perform authenticated actions under the authentication of the victim. So in this example, there's a victim going to cutekittens.com. Unfortunately, if you go to cutekittens.com, it might not always be a good actor. So it might be like a malicious actor trying to, for instance, steal some money from the bank. And in this specific attack, it will try to do this by including a resource through an image that will trigger some action in the name of the victim. And this works because cookies are implicitly included in third-party requests. And well, although this issue looks fairly simple, there have been many issues detected at very big companies like YouTube, Netflix, several banking websites, and so on. So one way to mitigate this problem is to have like a token in a form or make certain things unpredictable. But it's very difficult to do so across all the assets of a company. So that's why we have a thing called same-site cookies. So it's a basic cookie. It just has an additional attribute called same-site, which is instructed by the server. So the server sets this additional cookie attribute, and it needs to be enforced by the client. So there's two options for the same-site cookie. So on the one hand, there's strict, which makes that cookies will never be included in any cross-site requests. So only first-party accesses will allow this cookie to be sent along. And then there's the same-site lax cookie, which is the same as same-site strict, but has a few exceptions, such as a top-level get or a pre-render. And well, same-site cookies have been have existed for some time, or at least the specification of it. But I believe that once Google Chrome and Firefox and others will make this the default on the web, I hope that, well, it will change security for the better. So Chrome will start doing this from starting from version 76. So if we go back to our original example of the victim browsing to cute kittens, so if we assume that the victim first does some operations with the bank, and this bank sets two types of cookies, so a regular cookie and a same-site cookie. Then when the cutekittens.com tries to perform the attack, the browser will only include the cookie that is not same-site, so the regular cookie, and the same-site cookie, if it's used for authentication with the bank, then the bank will not be able to authenticate this victim, and so the funds will not be transferred to the malicious party. So, as I said before, we did this evaluation of these third-party cookie policies, but why should we do this? Why can't we just trust the browsers that they are doing what we expect them to do? Well, we know that browsers exhibit inconsistent behavior. So sometimes they deviate from the standard for certain things. And also, browsers are very complex, and there might be certain side effects of specific features that may cause unexpected things to happen. And on the other hand, for the browser extensions, they've been known to have been bypassed in the past. So, for instance, websites like Pornhub exploited the WebSocket mechanism to circumvent ad blockers. So, for these reasons and a couple of others more, there's a need for a comprehensive evaluation of the effectiveness of these cookie policies. And for this, we created a testing framework which had a certain amount of requirements. So first, we wanted to make sure that this framework would be able to test the browser in a black box perspective. Because for us, the source code of browsers is not always available. And even if it would be available, there's millions of lines of code for each browser that I don't think anyone would want to go to manually. And on the other hand, we also wanted to evaluate the more implicit cookie policies imposed by the browser extensions. So our framework had to support them. And so we came up with something like the following. So on the one hand, we had a browser instance, which is a browser configured in a specific way that had a certain amount of extensions, or might not have had an extension. And this we point at our framework, and out of the framework we should be able to determine whether there were any bypasses or any issues. So the global overview looks a bit like this. So on the top left side, we have our browser control, which instructs the browser instance on the right. So for this, we used WebDriver, and for browsers that did not support this, we used the command line interface. This browser was pointed to a number of different test cases. So on the bottom, you can see that we have a test generator which tries to trigger requests in all kinds of different ways. and these were served to the browser, and all traffic of the browser was intercepted using a proxy, and by analyzing the traffic that passed through this proxy, we managed to evaluate whether things that went through were the things that we expected to go through. And if there was something unexpected, we considered it a bypass or an issue. So one of the important things of our framework is to be able to generate different test cases. So we wanted to evaluate all the different mechanisms that can be used to initiate a request. And these can be from many different categories. So we evaluated 7 different categories from application cache, which is still, well, it's deprecated, but it's still supported by most browsers. The different types of HTML tags, like script, image, link, but also more exotic ones. Also, different headers may be causing the browser to send an additional request. So there's a link header, or if there's a violation of the content security policy, it might report something to an endpoint, and this will also trigger an additional request. Then there are also different types of redirects, like using the location header, or using a meta tag, or setting the window.location property. Then in JavaScript, there's also many different ways to send a request. For instance, using the fetch or XHR, or more lesser known things like event source. And then maybe a bit surprising one was JavaScript from PDF files. So this also can be used to send both GET and POST requests. And then finally, using the Service Worker API, it can also be used to send requests. So once we had all these test cases, we took a bunch of browsers and many different extensions. So I think more than 30 extensions and 7 or 8 different browsers. And we then evaluated whether the explicit and implicit cookie policies were well, correctly enforced by these browsers and browser extensions. So moving on to the results. Well, surprisingly, we found quite many issues. So for instance, the option to block third-party cookies could be bypassed entirely in Chrome and Opera by using the mechanism to send requests in PDFs. Then in Safari version 10 and Edge version 40, we found that actually the option was there, but it didn't have any effect. So it might give users like a fake feeling of being secure. Then also the features that were built into browsers also didn't work as well as they should. So there's, well, both the Opera ad blocker and Firefox tracking protection had several bypasses in different categories. So for instance, for the Firefox tracking protection, by adding this header, so it's a response header, it would trigger a request to tracker.com, and it could not be blocked by the built-in tracking protection. But the results were even more surprising for the browser extensions. So we found that all of the extensions that we tested, so more than 30 from different browsers, could actually be bypassed. And there were 3 main reasons why this happened. So on the one hand, there were design flaws to the ecosystem of these ad blocking and privacy extensions. So, for instance, in Chrome, PDFs are rendered as part of an extension. However, it's impossible for one extension to intercept requests from another extension. So this means that all requests triggered from a PDF in Chrome would not pass by the blocking extension, so they could not be, these requests could not be blocked. And yeah, also in other browsers there were certain types of requests. For instance, in Firefox, the favicon could not be intercepted by the extensions, which meant that all the requests went through. And then another category of where things went wrong was that the API and the documentation around this API was sometimes unclear. So, for instance, requests triggered by service workers or application cache had the tab ID that was associated with it was set to -1 in some cases, or for certain browsers. So this made it difficult for developers to figure out whether they should actually block this request or not. And some of the extensions did not block it, which allowed, or which would allow an attacker to bypass them. And then finally, there were some common mistakes made by the extension developers. For instance, they didn't request permission to intercept the WebSockets, which meant that well, by using these WebSockets, the extension would be bypassed. So to go a bit more in detail of how the design flaw of the PDF